Welcome back to Prompt and Paradox. In the last video, we had discussed that large language models, which are the brains behind tools like ChatGPT, don't read words, they read math. And their entire understanding of language rests on something called embeddings. An embedding is just a long list of numbers, a vector, that gives a word or an idea its precise coordinates on a massive, invisible, semantic map of meaning. So close coordinates mean similar meaning. But how does the neural network actually create these numbers? It's a 4-stage process inside the neural network. And we are going to break down this technical pipeline step by step and reveal the brilliant math that converts messy text into high-fidelity AI thought. The very first step is tokenization. The LLM can't deal with millions of full unique words. Imagine the size of internet. So it breaks the input into smaller, efficient units called tokens. Most of these models use subword tokenization. It will allow the model to understand complex words like unbannable by recognizing the meaning of its components part, un, ban, and able. This makes it more flexible and efficient. Each token is assigned a simple numerical ID. This ID, for example 1502, is just a label. It has no meaning yet. It's just the key that we need to start the next stage. The token ID then enters the embedding layer. This layer is essentially a massive learned lookup table, the first major weighted matrix in the LLM. Think of the embedding layer as the model's initial dictionary of meaning. When it retrieves this vector, the word vector, it's getting the average, context-free definition of the word. And through training, all these initial vectors have been placed close to related words. For example, dog is placed close to canine, but they still lack any sentence-specific context. Before we go further, we need to introduce the transformer. I'm sure you must have heard about it. This architecture, which powers all modern LLMs like ChatGPT, is a revolutionary design. You know what the core magic is? It doesn't read the sentence word by word. It processes every word simultaneously. Here is the major hurdle. Since the transformer architecture processes all the words simultaneously, it will lose the word order. And if we stopped here, the vectors for dog bites man and man bites dog would be mathematically identical. Why? This is because we still do not know the context of the word dog in the first sentence versus the another. In the first sentence, the word dog is a subject, and in the other one, it becomes an object. How would you know that? We inject positional encoding. This is a secondary vector, calculated using precise math based only on the word's position in the sequence. So we literally add this vector to the initial word vector. Think of positional encoding as a digital timestamp. It tells the model this is the meaning of dog, and it is the first word in the sentence. This is a vital information. You know why? Because it allows the LLM to understand the difference between subject and object. Now this combined vector, the word vector and the positional vector, enters the transformer block. This is where the model gets rid of ambiguity and adds context. Think of the transformer block as the contextual classroom. All the words in the sentence are allowed to look and talk to each other to figure out their precise meaning. This process is called self-attention. The vector for the word bank asks, which other words here are the most important for figuring out my true meaning? And when it sees river, it pays high attention to it. and mathematically borrows some of the meaning from the river word vector to refine its own coordinates. This means the final vector for bank in a river context is now mathematically distant from a bank in a money context. It is no longer a dictionary word. It is a context-aware idea. But how did the network learn the initial values? And how does it keep improving after every conversation in the transformer? That is through pre-training on trillion of text tokens. The LLM is tasked with simple goals, like filling in a missing word. So if the model predicts was, but the answer should be is, it has made an error, and that error is measured by the loss function. The goal is to minimize this error, and the error signal is sent backward through the entire network in a process called backpropagation. Using a technique called gradient descent, the model figures out exactly how much to adjust every single number in its massive system. Gradient descent tells the model, can you move the vector coordinates for France by this tiny precise amount so that the overall error is reduced on that sentence. This cycle of prediction, error, and adjustment repeats for billions of examples out there on the internet, continuously sculpting and refining the coordinates of the embedding map. The final result is an incredibly precise, contextualized embedding. This vector doesn't just represent a word, it represents a refined idea, placed perfectly on this map of human language. And because language is now math, the LLM can answer complex questions simply by performing linear algebra. For example, calculating the distance between vectors. The closer the distance, the more related are the ideas. This complex pipeline is the foundation of all modern AI. If you found this breakdown of the neural network helpful, hit that like button and subscribe. What part of the LLM architecture should we demystify next? Let me know.